being said, today we're going to start with sort of the module on experimentation and a little bit on causal inference. Before that, a few quick announcements. So obviously today is virtual. We have in-person class Monday at the regular time in the morning. To make up for this past Monday's canceled class, we have a guest lecture at a non-traditional time, 6:15 to 7:30. It's going to be more on marketplace experimentation. Hannah, she's great. She has a lot of experience with experimentation at places like Airbnb and Open Door, and also thinking about it academically. I know I've been trying to release homework 4. I'm still putting the finishing touches on it. It's going to be a short homework. It's not going to be, it's probably going to be like half or less than half the length of the regular homeworks. We'll release it by Friday, and you'll have, I guess, then a week and 4 days or something, week and 3 days to do it. But it will be shorter. Last thing, canceled office hours today, but I have extended office hours on Friday, 12 to 1:30, and then I'll also have extended office hours next week. And then Gia has office hours on Friday. Okay, cool. With that all being said, let's dive into experimentation. So, the idea of experimentation is a simple one. So this comic from XACD that came out, I think a week or two ago, which without the idea of clinical trials or experimentation, the old way of doing something was to come up with a new idea, to convince people it's good, and then just adopt the idea, right? So like the convincing people it's good takes the place of actually checking that it's good. And the idea of experimentation is before you launch the idea to everyone, you want to check whether it actually works. Maybe a second motivation, or, so that's a brief description of what experimentation is. Maybe some motivation. This is a tweet from Susan Apey. She's a professor at Stanford, and almost certainly will win the Nobel Prize in economics in the next 5 or 10 years for her work in sort of causal inference and a whole bunch of other areas. And sort of this is her saying that probably, and so this is she's an economist, so this tweet is specific to economists, but it applies to basically all data scientists. It's probably the most commonly used empirical skill in marketplaces, or basically any societal system, or like basically any online system or system as a whole, are those from experimentation or causal inference, which you could sort of is trying to approximate experimentation without actually doing the experiment. And sort of if you're trained in those skills, or can at least understand how decision making is made with those skills, that brings a lot of value to companies and to the system that you're in. And then maybe the last motivation is just the the empirical fact that modern companies use experimentation everywhere. And so certainly they extremely large companies like Google, Microsoft, Airbnb, whatsoever, each have hundreds or thousands of experiments live at any given time. And so right now, Google is probably testing it, Google across the company is probably testing thousands of different products and giving that to a subset of its users. And then even Google search is probably at the moment having 100 different experiments live. Can someone mute whoever is not muted? Thanks. Okay. So yeah, and these companies test everything from user interfaces, trivial things like user interfaces, to pricing and recommendation algorithms, to headlines on news websites. And sort of this is probably the most infamous example is Google tested 41 different shades of blue to test the color of the links for their search results. So they I don't know when this was at this point, probably 10, 15 years ago. And they had 41 different colors they wanted to test. They gave each of those things to approximately 2.5 percent of their users, and then they just measured things like click-through rates and things like that. And the blue that you see on your search results today is the winner of that test, right? So experiment, like sort of these modern online companies really are run by experimentation. And so understanding why you should do an experiment, how to analyze the results of an experiment, and when experimentation can go wrong and sort of needs more fancier techniques is vital to being an effective data scientist or product manager or whatever have you at these companies, or at any other system that hopefully is using experiments to make decisions. Any questions on the quite extended motivation? I know it's a little harder with online, but sort of it would be great to have participation. But that being said, I'm gonna on Zoom, I pinned my video, and like, if you're not comfortable with your face being recorded, then like, please, you're welcome to keep your screen off when you ask questions and things like that. You also, like, I'll maybe pause now and then to like check the chat if you just want to ask questions through the chat, and then I'll just read your question out loud and then answer it. So yeah, participation would be great. With that being said, are there any questions? Okay, then let's actually jump to the overview of the module. So, we've, I guess, already started this, but so today is the basics of A/B testing. So why experiment, and then common mistakes, and then, why experiment, and then how to do basic A/B testing, and then common mistakes in running and analyzing tests. And then next week is going to be A/B testing in social networks and marketplaces. So there's sort of in these online settings, when you have two-sided marketplaces, or when you have capacity constraints over items, or you have a social network on which you're running the experiment, you can't just do a very simple A/B test, because sort of there's, yeah, I'll get into it next week, but essentially you can't separate out your treatment group and your control group. We'll also talk about experiments over time and space. So, like pricing algorithms make changes over time, and so how to deal with that, and then maybe a little bit on adaptive experimentation. And then Monday evening, we have, like I said, this guest lecture on sort of more on experimentation and decision-making in two-sided marketplaces. And so we'll give some more detail on interference and maybe what to do, and advanced experimentation techniques on what to do about it. And then sort of time permitting, we'll get into a few other topics in causal inference and experimentation. So I know for those of you in urban data, y'all had a lecture on causal inference last week, which is essentially sort of what the professor covered was, given, like, let's say you have confounding or sort of reasons to run. So yes, so you have some historical data that you cannot run an experiment on, and how do you still try to maybe mimic an experiment or still try to learn the things that you would try to learn from an experiment without running an experiment? I might cover a little bit of that in this class, but the focus on this module is actually going to be sort of what can you actually do if you can run an experiment, and just because that is actually a dominant mode in a lot of like these online people-driven systems, sort of unlike healthcare or unlike criminal justice or unlike a lot of like super sensitive offline systems that maybe it would be extremely unethical to run experiments on. Okay. Yeah, and so some of these other topics, so what I might actually spend some more time on is sort of broadly what I'm calling experimentation culture in companies, sort of what gets complicated when you run many experiments over time and you're making many decisions, and now you have to think about trading off, sort of sample size in one experiment versus another, and so on. Okay, so before I get into how to run an experiment, let's briefly talk about why do experiments. Again, for those of you in urban data, some of this will probably be familiar from the lecture Emma gave last week. Okay, so what are the various ways one can make decisions? You know, for much of human history and maybe today, it's sort of the dominant mode is HIPPO, which is just like the highest paid person's opinion, right? So like whatever the boss thinks, that's what we're gonna do. But you know, of course, there's many different versions of this. There's the most charismatic person's opinion, which you're in a group discussion and the person who can convince everyone else sort of wins out. You can vote, you can have a consensus, you can have just majoritarian opinions. And you know, there's many places where these sort of decision making are the right thing to do, right? In a lot of democratic societies, we have this normative belief that some decisions should be made democratically with some protection for minorities, right? So there are many other ways to make decisions, and experimentation is just one of them. And besides people's opinions, you can also go through a structured, logic-based decision-making process. So try to have a structured discussion of some kind. You can also try to use past data to guess at, if you're trying to guess at the effect of the decision. So if you're, thinking of launching a product, try to use historical data on similar products to guess at the effect. And like I said, all of these have their place, but sometimes these decision-making tools aren't enough. That sometimes you just need to test if something works before you launch it to 1 billion people. Okay. And so why do some of these things not work? Or in particular, why does using historical using historical observational data not work? And again, those of you who are in Emma's class last week probably sort of learned that observational data often can be used, but it's often extremely challenging to use. And there's like a lot of things you have to get right in order to use observational data correctly. And okay, so what is the central challenge? The central challenge is confounding, and I'll walk this through with an example. So suppose you're a data scientist at the New York Department of Parks and Recreation, and you have data on which trees fell last year, right? So the Parks Department, I think, takes care of almost 1 million trees a year, and some of them are going to fall down before they're supposed to. And you have data on which trees fell down. And you want to answer the question, did we do preventative maintenance on the right trees? Right, so the Parks Departments, of course, do it like putting work into a bunch of the trees. They can't put work into every tree, and so they want to answer the question: is the trees that we put work in, did we do it on the right trees? And in particular, maybe another way to say this question is they have some decision-making process to identify which trees need work, and they want to know is that decision-making process good? But then if you're in this situation, you might look at the data, and what you would probably find is that trees that you did preventative maintenance on were more likely to fail than trees on which no work was performed. And if I just look at this correlation, what you might conclude is that you did work on exactly the wrong trees, right? You did work on the trees, you would look at this data and you might conclude that like your work actually led to more failures, right? That like the things that you did preventative maintenance on were actually were still failing, and so like your work was bad. And so like what happens when you look at this data and you find that correlation? Okay, before I maybe give exactly what's happening, let's just do a few other examples. So now suppose you're a data scientist at a subscription-based company, for example, Netflix. And so how do subscription-based companies work? You pay once a month or once every X weeks, and then you have presumably unlimited usage of the product for that company for that month. And okay, so you're a data scientist, and you know that someone else at the company, maybe not you, has been running a promotion. And what that other team does is it identifies the people who the model predicts, sorry, I say likely to fail, but are likely to quit the service. And then it sends them a discount, right? So you first identify who's going to leave who's going to leave, and then you sort of send them a discount so they don't leave. And then you crunch the data and you find that a higher percentage of the people who are sent a coupon quit than the percentage of people who are not sent a coupon. And so just like in the trees example, you might think that sending a coupon is actually counterproductive, that people are more likely to quit if they get a coupon than not. And then, you can come up with all sorts of like pseudo-psychological explanations for why that happened. And so what happened? Are there any questions so far? Okay, so then I'll move on. Okay, so such correlations are everywhere. So daily death rates are higher inside the hospital than outside of it. People who receive ads for smoking are more likely to smoke today than people who don't receive some ads if such ads are personalized. And so what's going on? Like why are these correlations the exact opposite of what one would think if we think that our interventions are working? If we think that preventative maintenance actually prevents failures, or that hospitals prevent deaths, or coupons prevent people from quitting a service, then why do we see these correlations? What's going on? And so, one hypothesis is that maintenance is causing tree failure, hospitals are causing death, and so on. But that's probably not what's going on. What's going on is, of course, the often repeated phrase, correlation doesn't equal causation. And in particular, what do I mean by that is in each of these cases, we don't know if the intervention caused the bad event to happen. All you know is that the intervention that the bad event happened to the same people or to the same things that you did the intervention on. But you don't know which way the causal direction went. Oops, my phone is trying to wake me up. Sorry, it is 7 a.m. here, so my phone alarms are going off. Okay, I'm back. Yeah, so in each of these cases, we don't know if the intervention caused the bad event to happen. What's the more likely explanation? The more likely explanation is that our past decision makers, the people who decided which trees to inspect, people who decided to go to the hospital, people who decided which people to send a coupon to, it's more likely that they actually did a good job at identifying who or what needed help, right? That I actually did maintenance on the trees that were all actually on the verge to failing. And in that case, the treatment helped. So the hospital actually, helped some people, or, prevented some of them from dying or delayed their death or so on. But of course, no treatment is perfect, right? You can't prevent all death. You can't prevent all death. You can't prevent all people from quitting your service, even if you send them coupons. You can't prevent all trees from falling down, even if you do maintenance on them. This explanation is exactly sort of cause the correlation. The people who are selected into, one sec. Yeah, yeah, so the connection seems a bit unstable. So let me actually repeat what I just said. Sorry, I am on really bad hotel Wi-Fi and my hotspot is unreliable. I will switch to my hotspot if this doesn't get better. So please let me know if this remains bad. Okay, so yeah, so let me back up a little bit and repeat what I said. So in each of these cases, we don't know if the intervention caused a bad event to happen. More likely it didn't. More likely what happened is the people I did the intervention on, the people I sent to the hospital or sent coupons to, were actually more likely to to actually be sick or more likely to actually be likely to quit. And so even if the intervention was completely useless, even if it did no harm, if it was completely useless, we would still see that the intervention is correlated with people who are more likely to quit. And that's just because that correlation is by design, right? We actually, those are the people we want to send coupons to. And then if the treatment, helps a little bit, that, conditioned on getting the coupon, you're less likely to quit, but you're not perfectly, the treatment isn't perfect, then the correlation will still go in the direction that we observed. Are there any questions here? Okay. And I just want to point out that this should be, I'm calling this confounding here, but it's sort of what the challenge is exactly what the challenge was in polling, right? When you had unobserved selection bias, that people who are likely to answer the phone are more likely to have one belief than another belief. And the same thing is going on here, but just in all sorts of other systems, right? The people that you're sending a coupon to are more likely to be the ones who are quitting than not. And so the central challenge is that the past data doesn't tell us easily what the counterfactual was. What would have happened to this tree if I didn't do work on the tree? This is also called the potential outcome. So actually the Nobel Prize in Economics for this year was partially awarded for developing and expanding this counterfactual framework. So this is called the potential outcome, right? Is to what would have potentially happened? What would the outcome have potentially have been if I did something that I didn't actually do? And there's many observational techniques to try to measure this counterfactual. And for those of you in urban data, you discussed some of these last week. And like I said, the Nobel Prize in Economics this year was partially awarded for developing really to do to convince people that you did them right. And so if you can avoid doing them, you should avoid doing them, and you should run an experiment. And like I said, that's what modern companies, modern online marketplaces and other systems do, is they just run experiments to get around this problem of observational data. And so I know this has been quite an extended motivation, but sort of the idea is that experiment us around this problem of confounding and question the motivation. Feel free to type in the chat. So if you don't want to unmute or turn on your video, I'm happy to, I actually did set it up so I can see the chat. And so feel free to just type in questions in the chat throughout.
I don't know if you said this, but I didn't, because you cut out a little bit, but for potential outcome, how do they go about trying to measure that?
Good question. So I don't want to sort of do too much right now on that. I might say a few words next week, but sort of there's so like the one I'll describe now is maybe they use something called an observation, sort of a natural experiment. And so, for example, even if you didn't actually try to do an experiment, sort of like, you know, the most classic type of natural experiment is often like rounding. So for example, let's say in ride hailing systems, they show you some price that's down to, you know, like, you know, some dollar and some cents. And that price is rounded from some, like, you know, super precise. So let's say there's a search factor of, like, you know, they can do a search factor of 1x, which is just like standard prices, or they can do a search factor of 1.25 or 1.5 or 1.75 or so on, right? And so they have discrete chunks. And even if they didn't run an experiment in that they sometimes randomize whether you got 1x surge or 1.25 surge, in sort of what they know internally is that, like, right, they calculate that number that says that presumably rounded to, like, you know, 1 or 1.25. And then sort of then on either side of the rounding, sorry, I think my internet is unstable again, so I'm going to pause. Okay, so Jia just told me that I'm cutting out very frequently, so I'm going to try to, sorry about this, I'm going to try to move to mobile hotspot, and then that should be better. And if that doesn't work, then I will switch to audio only. But I don't want to sort of switch to audio only if I can help it. Okay. Hello, can everyone hear me? People can hear me? Is this audio better? Okay. So I'm gonna proceed as if this is better. And, you know, I'll just pay the hotspot bill when it happens. Okay. Yeah, so okay, so the yeah, so like I was saying, the you know, there's internally the system thinks that search should be, you know, sometimes it thinks search should be 1.123, and sometimes it thinks it should be 1.126. And those two numbers, if I did my math correctly, round differently to 1 and 1.25. But like, you probably don't believe the last decimals. Like those last decimals are just like essentially random, right? And so what that happened is a natural experiment cost to rounding. It's two people who are like otherwise nearly identical. Like the search system thought that search should be around 1.12. Some of them as a 1, some of them get treated as a 1.25. Right, so that's what's called a natural experiment. There's also ways to sort of try to calculate these potential outcomes with no with no randomness at all, but that becomes even harder. Okay, so there's a question in the chat: how can this sort of experimentation be adapted to complex systems? We're gonna try to give a partial answer to that next week. Or in that we're going to talk about, you know, experimentation to two-sided marketplaces and a lot of other systems where you can't do the basic A/B testing that I'm going to sort of discuss the rest of today. Okay. Are there any other questions here? Okay, cool. So I'll move on. Okay. So that was the challenge with confounding. So like, why do experiments help? So let's say you want to answer, would this customer have quit if I didn't send them a coupon? And unfortunately, you can't, even with experimentation, you can't get the potential outcome for both for both sending them a coupon and not sending them a coupon, right? You can't send the same customer a coupon and not send them a coupon at the same time. And, you know, like the maybe, but, you know, the devil's advocate ones of you will say that, okay, maybe I can send a coupon this week and then not send them a coupon next week. But then I'm going to be even more annoying and existential and say, but then you're a different person this week and next week. And, you know, read some philosophy and then you'll be a different person. But yeah, so the point is you can't you can't both, like the same person at the same time. You can't have that. You can't both send them a coupon and not send them a coupon, both send them to the hospital or not send them to the hospital. But what you can do is you can take two otherwise identical customers and only send one of them a coupon. And to make sure that you had no selection bias, randomly choose which one you send them a coupon to. And so you have two customers who a priori were exactly the same. And then one of them you sent the coupon to, and then one of them you didn't. And then if you do this for enough customers, so if you do this for, you know, you don't send them a coupon, then you just measure the fraction of people in each group that quit. And sort of the idea is that randomizing between people breaks the confounding. It breaks the self-selection. Smart, and they probably were pretty effective at identifying who needs a coupon. But if they were identifying, is my internet unstable again? Is my audio bad? Okay, I'm gonna try to turn off video for a little bit. Actually, can I ask all of y'all to turn off video first? And then if you have questions, just type them in the chat. And then maybe my internet will be better. I really apologize about this. Okay, so randomness breaks the confounding because, you know, presumably your fellow data scientists were smart and were more likely to send coupons to people who needed it. But now, sort of by randomizing between two people who are equally likely to need a coupon, you sort of break that confounding. Yeah, and so, you know, there's a question in the chat, what are the moral implications of this? So like in the medical setting, giving one person a potentially useful treatment, another person not. And so I think that's a deep question that's hard to answer in sort of in the abstract. So like even in the medical setting, where one would think this experimentation is like the most challenging, like we do this all the time, right? Like this is exactly what a clinical trial is with the placebo. You give half of the people a vaccine that you're testing out, and the other half you give a placebo. And you know, there's of course like a million regulations and oversight to make sure that this is done ethically. You know, there's of course a long history, you know, including in the United States, of sort of doing this unethically, sort of, you know, taking advantage of, you know, underrepresented minorities, you know, Black people, like sort of, you know, otherwise socioeconomically disadvantaged people, and withholding medical treatment from some people, and, you know, and and giving medical treatment to sort of more privileged people. And so there's certainly huge moral implications here. There's like definitely a lot of ways to like mess up here and like, you know, do this unethically. But at least in medicine, it's possible to do it. And then in online marketplaces, I might share some papers and some resources later on. But like a similar thing happened, like, you know, I have a question to ask in any given setting, right? So like, is this sort of the intervention that you're testing in your system? You know, maybe you don't go through the same process that the medical community has decided is the sort of is the process to do this in medicine. But maybe, you know, it's worthwhile thinking through the ethics of that in your setting, like, you know, like what are like the implications of like sending some people a coupon and not sending other people a coupon and so on. The benefits here is that if you randomize, you don't need to convince people that the selection bias didn't happen. You don't need to convince people that that this other team didn't actually send coupons to people who are more likely to quit. Because by definition, you randomized in a way to make sure that it didn't. And you know, there's a giant asterisk here, but I'll get to that in a second. And then again, at their most basic, these things are very easy to run and analyze. So I'll give an overview in a few slides. You don't need like much fancy statistics to analyze these things correctly. And then often in new systems, you have no past data to even try to make your decision on, right? No one has used this new feature that you want to decide whether to launch or not, for example. And so sometimes you might just need to experiment. And sort of these two asterisks are, of course, you know, these things are not all like these claims are not always true. We'll discuss some of these in detail starting next week. I might get to some of this sort of near the end of this lecture today as well. And I just want to point out that we've already seen an example in this class of randomization not actually working all the way, right? So the first module on polling was exactly this, right? So in the first module on polling, we, like most pollsters, and you know what we assumed right off the bat was you randomly decided who to call and who not to call, or you randomly decided who to text your poll or whatever. And that was done from like picking random phone numbers out of a phone book. But even though you randomized, we still had self-selection bias, and we still had to do all of these methods to try to eliminate sort of that self-selection bias. And the reason for that was because even post-randomization, some people answered the phone and some people didn't. And that sort of has a lot of analogs in general experimentation. That's called like you treated someone, you actually gave them, you know, the vaccine, versus you intended to treat them, like, you know, you randomized such that, you know, you wanted to treat them, but at the last minute they said they didn't want it or something. And then in that view of the world, sort of the first module that we did in this class on polling was actually one sort of this question was actually sort of an example of what to do in the presence of confounding or self-selection bias, right? So that was almost or that was exactly an example of the type of analyses you would need to do with observational data where selection bias exists. And I just didn't call it that, but that was what was going on. Okay. Any other questions so far? Feel free to type it in the chat or say it out loud. Okay, so I will move on. Okay, so with that very long-winded introduction on why to do experimentation, let's actually let's actually talk about how to do experimentation in the most basic case. So the core idea is very simple. You have an idea for a change in your system. You give some percentage, it doesn't have to be half. You don't have to balance, but you give some percentage of your users the old system and some percentage of your users the new system. And sort of a quick caveat here, I'm going to be loose in my language with whether, like, you know, the A and B refer to the two systems you're testing, being the old system and the new system. You can also think about them as just being two different systems that you want to test out, right? So like in the homework, the example will be we'll be using data from a news website called Upworthy, which is like sort of kind of like BuzzFeed, in which they're clickbaity news websites, and there's data on a bunch of A/B tests on testing different headlines. And so there's not an old headline and a new headline. There's just two potential headlines. But I'm going to be loose in my language here. Sometimes I'll say old and new. Sometimes I'll say A and B. Sometimes I'll say treatment and control. But the core idea is the same in each one. And so you should just like, and in real life, people also often like interchangeably use these words. And so you should just get used to sort of those words, like sort of being used interchangeably. Okay. So you give some percentage of your users system A and some percentage of your users system B. And then you decide what metric you care about, right? So for example, the metric could be click-through rate. How many people clicked on this headline to read the article and how many people clicked on the other headline? Or maybe it could be shares, right? So like Facebook shares. So how many people shared this on Twitter or Facebook versus not shared it. And then just check if your system improved the metric, or if system B was better than system A in terms of your metric. And that's it. This is all you have to do for A/B testing. Any questions here? Oh, yeah. And then finally, of course, you launch your product if good things happened, or you choose A or B, which one was better, and then that's the one you go with. And that's the idea. Okay. And so I basically already went through this example. Suppose you're a clickbaity news organization and you have two headlines you want to test. Your metric is the percentage of people who click on the headline. You give half the people one headline, the other half the other headline. You wait a day. You measure the percentage of people who clicked on each headline. You run a statistical test to see if the difference is statistically significant. And you choose the better headline, and you use that going forward. And I just want to point out here, I don't want to say too much right now. We're going to say more about this later on, potentially next week. Hannah's going to talk about some of this during her guest lecture. But I want to point out that, for those of you who've taken like a statistics, or I think according to the course prereqs and the syllabus, every one of you has taken at least one statistics class, should know the basics of significance testing. I'll teach some of this in the homework. Please come to me or during office hours if some of this is not understandable. But yeah, so you run. So I want to point out though that running a statistical test is very different than making a decision that's good, right? So if something is statistically significant, at the 5% level, what that means something very precise in statistical language, and that doesn't have to be that doesn't actually have to mean the same thing for whether it's good for your company to launch or not the product, right? So like, for example, if let's suppose in this last, like you have two headlines, and one of them is slightly better than the other in terms of the percentage who clicked on each headline, but the difference is not statistically significant. At the end of the day, this news organization has to launch some headline, right? They can't just have an article without a headline, or rather, an article without a headline is going to do worse than either one of these two things, right? So even if the test isn't statistically significant, they probably just want to launch something, right? And you might as well launch, for example, the one that did slightly better. even if the difference wasn't statistically significant. In the other direction, suppose you ran a really large test and you write like Facebook, right? Like Facebook can run tests on millions or tens of millions of people. And when you run that large a test, it's very easy to get statistical significance. If there's even the slightest bit of difference, right? So like, if like one change caused a 0.00001 difference in some metric, oftentimes that can be picked up in like a very precise A/B test. But if it's very expensive to launch that feature, if it costs $1 billion for the company to launch that feature, and the effect is actually very, very small, it makes actually very little difference, but it makes some difference and it was statistically significant, you might still not want to launch, right? So I just wanted to sort of say a few words there in this example, because I have it here. And that sort of oftentimes it's useful to run a statistical test, but I don't want you to confuse it with good decision making. Okay. Any questions on the high level idea, or on the high level idea before I? Okay. So I just want to sort of add a little bit of notation for this. This will be useful for the homework where we ask you to code things. Okay. Suppose we have a treatment and a control. So we're going to call treatment as x equals 1 and control as x equals 0. And we can call them another sort of, adding more language here, we can also call them arms. So we can call them the treatment arm and the control arm. And then suppose we have a binary outcome, right? Either someone clicks on the headline or doesn't click on the headline. And then sort of notation for the ground truth outcomes. So Y1 is sort of the fraction of people who click on the headline if they get the treatment. So if they get, for example, headline A, and Y0 is the fraction of people who click on the headline if they get control or if they get treatment B. And then what I'm going to call is the true treatment effect, or the average treatment effect, is Y1 minus Y0. So what this is what fraction more of the people clicked on the headline if they got headline A or if they got the treatment than if they got headline B or they got the control. And this is what we want to measure, right? So what we care about is this difference. We care about whether treatment A is better than treatment B. And so what we do, again, in this simple math example, is we give each arm to n people each. And then we get sample measurements, Y1 and Y0, which is the fraction of people who click on the click on the headline under treatment and control respectively in your sample. And so this notation should be, again, connecting back to the first module in the class on polling, so this notation should be familiar, so the fraction of people who click on the ad are, the top is the indicator for, the number of people such that they clicked on the ad given they got the treatment, divided by n, because n is the number of people who got the treatment. And then my estimate for the average treatment effect is just going to be y hat 1 minus y hat 0. And then I can run a hypothesis test. So in the homework, I'll walk you through running a hypothesis test. You can run a hypothesis test to see if this difference is significant, statistically significant. And, the standard approach is, of course, what most of you might have encountered in a high school or undergrad statistics class, is the difference is statistically significant if the p-value for the experiment, if the p-value for the difference is less than 0.05. And what I want to point out here is that this is, and just I want to emphasize what I repeated last time, is this is exactly the wrong, like sort of like this is not the right thing for decision making, but it is a standard thing to do. And the way that you could do it in Python is this like to run this hypothesis test is this thing in the stats model package in Python, and this test. One sec. So there was okay. So there's a few questions in the chat. Let me just read them and answer them. So the question is y underscore 0. So this control. What is this? Like what is the math for y underscore 0? And that math, so y underscore 0 is going to be the number such that y equals 1, given that x equals 0. And so the underscore, the underscore 0, or the subscript 0 refers to whether they got the treatment or the control. So they got to whether x equals 0 and x equals 1. Okay. The next question. If I have 2 features and 1 control group to test, would you just divide the population 1/3 for each group? That's certainly one way to do it. I mean, that would be the default way to do it. There's a big art to choosing the, and somewhat a science, to choosing the sort of the n for each treatment and control, right? So in this example, I just said that NP, like half the people in one, half in the other, but there was no reason to do that, right? There was I could have like 4/5 n in control and 1/5 n in treatment, and different companies make different decisions, and or for different experiments you make different decisions. There's a lot of reasons that I might not have time to cover too much in this class, but for example, you might want to do a power analysis, which is how many people. So for example, suppose you actually do have a treatment and control, where control is like what your company has been doing forever, for like the last 100 years. And so you already have a good idea of what your sales look like under control. And so the only thing you actually care about is getting a good handle on treatment. And so that might affect your what's called a power analysis, which is how many people you need to send to treatment and how many people you need to send to control. But yeah, it's like the naive thing to do with more treatments and the control is divide 1/3 each. And for example, that's approximately what Google did for that testing 41 shades of blue. They approximately just gave each color blue a different percentage. But like in the past, I've run experiments on an online marketplace, or designed an experiment in an online marketplace where like we decided not to do an even for treatment and control. So we had a control that we gave to, I think, 10% of users, and then we had 4 different treatment arms that we gave to 90 divided by 4, whatever that is, 18. No, I'm going to embarrass myself. 22.5. 22.5% of people each. And so that I think that is very context dependent. Okay. The next question. So is there any value in normalizing the difference relative to y hat 0? So and so if there's very small effects, they might get lost. Yeah, so I think, again, I think this, it's a good question. It's hard to answer in any generality, because sort of with small effects, okay, so let me sort of illustrate this with an example. right? So let's see, what's a good example? So the example I wanted to give, but I'm not going to give because I'm going to embarrass myself. And sort of, this is almost like a perfect demonstration of what I'm about to say is like this stuff can get confusing depending on different ways to normalize. And that, so like, you know, most of you at this point have probably read headlines or news articles that is like, you know, the Pfizer vaccine is 96% effective, or, you know, before the test, like, you know, compared, you know, before they were worried, or maybe they thought that these vaccines would be 65% effective or whatever. And like, I just sort of, I'm going to embarrass myself on what these numbers actually mean because I don't know what they mean, but I do know what they don't mean. Like these numbers don't mean that if you get, you know, if someone next to you has COVID and like you're breathing the same air, then that there's a 96% chance that you don't get COVID and there's a 4% chance you get COVID. Like in reality, the probability that you get sort of COVID is much less, like is much less than 4%, even if sort of, you know, if you know, even if sort of someone next to you, or you know, someone next to you outdoors or whatever has COVID, but rather what that number means is like some relative difference. Is that like, I think it's like 96% of that someone with a placebo got COVID in that encounter, someone with the vaccine would not get COVID. I believe that's what it means, but I'm probably wrong. And so like, don't quote me on that. And so like, I guess that's just being saying is like, sometimes treatment effects expressed in relative differences, like the question asked, like, you know, take some ratio. And I think that sort of in some circumstances, that's the right thing to do. And to communicate it that way. But you should just be very careful when doing that, and very careful in communicating to the people that you're communicating with exactly what any number means, right? So like, you know, this like long-winded example of like, you know, COVID vaccine effectiveness is like, you know, I would characterize that as a communication failure by like the news media on like communicating what these vaccines mean, is because, you know, even someone like me who like presumably knows something about experimentation and like, you know, reads reads news articles, I'm confused about what that number means, right? And so a lot of people are probably confused about what that number means. And so that's a long way to say that it oftentimes doesn't matter what measure you like, whether you're using like ratios or subtraction, as long as you're very clear to whoever you're communicating with what you're doing. Okay, next question. How can we apply the same math to non-binary outcomes? For example, like the outcome that we're interested in is like revenue generated from the treatment group. And so like in the most naive one, you could just do the exact same thing, where instead of Y being a binary outcome for each individual, you can just say Y is your continuous outcome. And then you have some average. So you can also take the average for that continuous outcome. So just take the mean response, and then you can take the mean difference. So basically, like nothing in this slide, or very little in this slide, is actually specific to binary outcomes. But then you would just run a different test. So this hypothesis test that, you know, that's implicit in the code sort of link that I have at the bottom, you would just run a different hypothesis test. Are there any other questions here or follow-up questions? Okay, then I'll move on. Yeah, okay. So another, I'll probably link this and like do a walkthrough of the homework about sort of A/B testing and like doing some of the code. There's like a nice blog post here that I linked to about how to do power analyses and to like, decide what n should be, and then actually like running the test and like analyzing the data in Python. Okay. And so, in theory, everything that I just said is very easy, right? You have an idea for a system change. You give of your users this old system and some percentage of the new system. You decide the metric you care about. You check if anything changed, and then you launched if good things happened. And so at the high level, this is a very easy process, but there's a billion complications about doing this well and doing this, like sort of making sure that you like, it's again, much easier than doing things with observational data, but there still are things that you can mess up. And so here in this slide, I just made everything in red, or, I'm sure there's other things you can mess up here that I didn't, maybe you just have a bad idea, but everything in red are like certainly things that you can mess up, or there's different choices in making. And we're going to talk about some of these in a little bit. Okay. And so what are some of these key challenges and like decisions you have to make? Perhaps the most important one is what is your objective and how do you measure it? And also, can you measure it? So for maybe to stay on the topic of staying on the news headlines, for those of you who've been following the whole like Facebook papers, Facebook leaks, whatever you call them, sort of stuff, one thing that came out in that is that internally Facebook, for like how popular the engagement of Facebook post is, values emoji reactions 5 times as much as it values a like. Actually, I really hope most of you are not too young to actually use. Does that make sense? Do people use like standard Facebook? Do I have to explain Facebook posts and like standard Facebook? Okay, no, actually, this is probably true in Instagram too. So most of you are probably see this in Instagram. So actually, I don't know if Instagram has different emojis. I'm too old. Okay, anyway. So in Facebook, so that they have sort of their measurement for engagement was that an emoji reaction, including the angry face, is 5 times as valuable as sort of a thumbs up reaction. And and then what these leaks or these papers are then claiming, and critics are claiming, is that sort of feeds like polarization and like anger on the platform, in that even the the angry face reaction is considered more valuable than a like. And like, so the claim there is that's like the wrong objective. Like if you have if you're testing an algorithm and the thing is that you want to maximize the number of angry face emojis, then that's probably like leading to like bad long-term outcomes on your platform. In that like what are the types of things that you're encouraging? What are the types of posts or engagements you're encouraging? Okay. Yeah, so that's getting the objective right is like almost the hardest thing, and it's the single most important thing. And Amy talked about some of this in her guest lecture as well. Okay. And so what percentage of the users do you give the treatment to? How long do you run the experiment? What if you have thousands of potential tests that you want to run? You can't run each of them on its own day independently. You have to sort of share the user time. You don't want to waste time testing things that are obviously better, right? So like there's a protocol in clinical trials, and I'll talk about this in a little bit, right? So actually, yeah, let me just talk about this in a little bit. And then how do you analyze the results, right? So like what sort of statistical test do you use? And then we've talked about this a lot already. What is the bar for launching the product? How much better does a new feature have to be in order to actually launch the product? Do you have a bias toward launching new features, or do you have a bias toward like not launching new features. And I want to point out here is that this can be different in different scenarios. So like in medicine, there's a high bar for a new medicine to be approved, right? Like in this, like a vaccine can't just be, like if the effect, it might not have been approved. But like even if the vaccine is better than a placebo, if it's not substantially better, it might not be approved. But in a lot of online platforms, it's actually the opposite, right? Like a team went through a year of, let's say you have a big feature and you go through a year of like designing the treatment, coding something up, like going through a bunch of approvals and so on. And then you finally run an experiment and the experiment's non-conclusive. But the experiment is just one piece of evidence, right? Like if the company invested so many resources for a year, it might have been because they have a high prior sort of belief that this experiment would do well. And so, or sort of this treatment would do well, this product would do well. And so experiment is inconclusive, you might launch anyway because the experiment doesn't like overturn your prior belief. But like the only potentially you would only not launch if like the experiment returns that this feature is terrible and substantially decreases engagement. Yeah, so I just want, so there's a lot of choices to make here on the bar for launching. And then next time, what we're going to in particular cover is how to run experiments and analyze experiments if you have interference between treatment and control. And so that's another challenge that I'm going to describe and get into next time. Are there any questions here? I know I have 7 minutes left. I can get into one common mistake people run, but sort of if there's enough questions for me not to get into that, I can just start off with that next time.
Hey, Nico.
Yeah.
Hello. Oh, yes. Hey, I had a question. Professor, excuse me. Did you say you were gonna talk about like the wasting time testing when one is obviously better? Are you going to talk about that next time, or I'm kind of deciding?
Yes, that's good question. So that's a little bit related to this peaking thing, and so I'm happy to just dive into that if no one else has questions.
Okay. I was kind of wondering what you thought of like the 42 Shades of Blue experiment. Just like whether, I think it seems like a little much to me, but
I mean, like they claim that it has, like in the sort of use, like, in basically any, it's just like one of those things that basically everyone uses as the example to introduce experiments, because it's like on the face of it, it's like ridiculous, right? Like just like, pick a blue and just move on. But, like it also demonstrates the usefulness of the experiment, right? Is that like sure, you can like ask a bunch of designers which blue to use, but like it's really hard to like there's no, okay, maybe someone who like studied graphic design in undergrad is about to like shoot me, but like there's like no theory that gives you precise enough answer to like this shade of blue is better than that shade of blue. And if like, but then we also know that like, some shades of blue are worse than others, right? Like, let's suppose they had like a really, really like bright neon blue that like hurt your eyes. Like you're not gonna like, most of you are probably certainly too young for, crap, I didn't even use it. What's the thing before Facebook? That social network. Anyway, that social network. Yeah. Yes. Yeah. So like they sort of allowed you to like sort of customize your own HTML and so on, right? And like there were some like ridiculous pages that people would do, and like like Web 1.0 was like just like bad design. And so like clearly we know that the design matters for like how much you end up using Google. And so like you're in a setting where like theoretical or like, principled reason to prefer this shade of blue over that shade of blue. And we also have some guess that it matters. Then like, if like billions of people are using Google and like interfacing with this, you might as like, it's like costless to run an experiment for 6 months or a week or however long they ran it.
Right. Yeah, that's true. Yeah, the scale is pretty costless. That's true. At the end, could you comment on your next the class you're teaching next semester, or maybe next class?
I'm happy to talk about that in office hours.
Okay.
But sort of like the sort of the one sentence summary is that it's a PhD class. I'm sort of like probably not going to allow many masters or like any master students unless there's like a demonstrated commitment or like desire to like want to move on to a PhD.
I see.
Yeah. Okay. Okay, so we have 3 minutes left, so I just want to do the motivation for like, if you don't want to waste time, and so like or a description of like this common mistake, and then I'll really dive into it next time. And so in modern online platforms, it's easy to see experimental results while they're happening. So this is a dashboard from a company called Optimizely that like really allows you to like plug, like, you can just like interface with Optimizely to run experiments on your website. And during the experiment, they let you see this sort of dashboard. Like so far, you've had 80,000 visitors, you've been running this for how many ever days, and then they'll show you, and so this is, y'all can't see my mouse, right? No, so okay, so they have, there's one control and 3 treatments, and then there's 4 different metrics: visitors, views. All right, so visitors is randomized, and then views, whether they clicked on the example. This is, I don't know what type of website this is, whether they clicked and whether they clicked on the picture. And then sort of what they showed you, like how this affected the metric, right? So does this increase views, decrease views, and so on. And then they did sort of, it's green if it's like statistically significant in the positive direction, and then it's red if it's statistically significant in the negative direction, and then it's sort of gray if it's not statistically significant. But you can see this while experiment's happening. And sort of what they noticed a lot of people doing was motivated by the following. So in the modern online setting, the approach I described of taking n people and like running it with the A/B with n people is incredibly wasteful, because you just know that you could learn with like the first 1,000 people that one feature is just like obviously better. And so what they saw people doing was people would just continuously stare at this dashboard. And then as soon as things became green or red, they would stop the experiment. They would say, okay, things are statistically significant, and I'm just going to stare at this dashboard and then stop the experiment. And with that being said, I'm going to stop this class at 7:55. And so next time I'm going to tell you why that might not be a good thing. So I guess while people are leaving, I just want to flash the announcements again. And there is a question in the chat that I didn't get to, and I'll get to it next time. So if I don't remember, please remind me next time as well. But with that, thanks for showing up, and thanks for being patient with my technical difficulties. And see everyone in class physically Monday morning.